I'm hearing weird stuff.
All right.
Hear that? Ding. I'm getting bored.
Yes, the Q&A is working.
Yay. I can't hear them.
Yes, we can't hear them, but they can type, which is weird.
Oh, cool. So I don't have to use these anymore.
However, it says that there's no viewers. It says 0 viewers, but 2 people just said that they're... Yes, it does work. However, there are only 2 viewers.
What's this?
Let's wait until the other people show up.
So what are you going to do? Can you go down so I can show you something cool? On the other side, on the other one.
What?
Go over there.
It says questions, answered questions, and spam.
You go somewhere else, Dad. I wanted to show you something.
Hold on.
Fun.
All right, now it says that there's 2 viewers. All right, let me try to arrange things so that this works. Okay. It's someone. Justin said, "Are you supposed to hear us?" I thought that I would be able to, but I think that only works if you are guests. But I don't know how to make you guests. I have on the control room thing, and I think that you're viewers, not guests. And I don't know how to invite you. I'm sorry about that. But yeah, so you'll have to type in your question. Yeah. Oh, someone says they can't see any video. They don't expire after a while. I have to click on them and then they expire. So someone says that they can't see anything. Let me do my screen sharing. Share. Whoa, look at that.
Whoa, what?
All right, let's do this.
Screen sharing?
Screen sharing means that they can see what I'm seeing. All right. Someone says, I think I'm viewing. Let's go back to the screen for a little bit until we get more people coming. Let's hide this.
Whoa.
So we got 7. Now, Jack, okay, now you can't talk anymore.
Why?
Because I'm about to do the class now.
Oh, but I want to hear too.
Actually, let's...
Yeah.
Okay, so listen, you got to be quiet.
Okay.
Elijah says, I think I'm viewing. Yes, I think you are viewing too. Okay, we have 9 people. Before, there were 15. See, there's 15 right here. So we'll wait for a few more people to come over for the new one before we get started. All right, 11, and we'll get started with the actual class. I'm just sitting here, hanging out.
Dad, can I show you the funny thing now?
No. We're talking.
It's really funny.
13 viewers. All right, I think we'll wait for 2 more people. So we got 15 here, so we just need 2 more, and then we'll be ready to go. This, by the way, I think will be archived. Ah, yes. All right. I'm very glad you can see the video now. I think I forgot to press a button. It says that there's still only 13 viewers. I want to wait just a little bit more for 2 more people, because before there were 15. Yeah.
The vacuum.
All right. Okay, so we got 14 now. I think that's going to be it. All right. Hi, everyone. Sorry for the craziness getting the Google, Hangout thing working. It's pretty snowy where I am, so I'm glad that we're able to do this. If you click on the Q&A thing, I think it's on the left. Maybe it showed up immediately when you turned on the viewing thing. You can type stuff into the right, and I'm going to set up my window like this so that I can see your questions, and I can see like code that we're going to write together. The goal for today is just to review designing basic objects in Java. Last time we talked about making simple programs in Java. You know, we talked about functions and methods and stuff like that. But here I thought that what we would do is write both kind of as a review process, but also to talk a little bit about how we'll think about programs in this course. We're going to implement two data structures, the essence of a list and the essence of a binary search tree. The list will use that example over and over and over again in the course, and the binary search tree will be particularly useful for implementing your finite sets. Can someone tell me that I'm going a good speed and you can see the code as a question? Then that'll tell me that I can move on. No one is doing it. Ask your audience to submit questions. Please submit a question that says, you are doing it at the right speed, and I can see the code. Questions, answered questions, questions.
No questions. I think they're ready to go.
I don't know. I just want to make sure. Oh, did I turn off the screen share?
Yeah, I think you just did. So
okay, let's share the entire screen.
okay.
Right, there we go. So right now, even though I'm sharing the screen, I present everyone. Okay, good. So Paul says he sees it. So Justin says it's okay. Paul says it's okay. Everything's okay. All right, very good. All right, thank you. Okay, so as before, we've got to be able to run this program. So I'll write class C3, public static void, main, string args, a little bit smaller, close, and then we'll write down system.out.println test, and we'll hit run to get it. Now let me close these things.
Dada.
Jackie can't talk while I'm teaching.
I want to tell something, Dada.
And for all of you who can't see me, my son is sitting right next to me. If he keeps bugging me, I'll have to make him leave. All right. We just have the essence of something that can run. So what we're going to do is we're going to write down a function to keep track of some numbers, or write down a data structure to keep track of some numbers. Let's say that I want to keep track of the ages of my kids. And their ages are 6, 4, and 2. So I want to have a list that has 6, 4, and 2 in it. So at the end of the day, I'm going to want to have a function that I can call that, let's say that it says the total age. So total age is this, and we want to end up creating something called kids. So total age kids dot total. We'll call this function. And we want that to be 12. I like a plan. Okay. So the list that you implemented when you were in the 101 course, you started off with a data definition. And the data definition you wrote was something like this. A list of numbers, or let's say a list of ages, is either an empty list of ages, which you wrote down as empty, or a cons of ages, which you wrote down as cons age, and then list of ages. You write down something like that. And empty and cons were built into the language, and so you didn't have to do anything to turn this data definition into part of the program. Now, using this data definition, we could type in what we want, right? We could type in right here, cons 6, cons 4, cons 2, and empty. However, notice that I wrote that in Racket, and so it's not going to work inside of Java. But what I can do is I can slowly turn this into a Java program by working from the inside out. So we'll take this right here and we'll cut it, and we'll say girls, because my girls are all the youngest ones. Then I can cut this and say baby, and then say list baby equals that. And then I'll say list honeymoon for empty. And then I'll take that right there and put it for the empty. So now what I've done is I've taken all the different pieces of the list that I ultimately want to make, and I've turned it into the sub-expressions. Now, that's going to make it easier to convert this into a Java program. Now, what Java makes us do is it makes us do two things. First, in front of every data type, every data instance, I write new. So I say new empty, new cons 2 with honeymoon, new cons 4 with baby, and new cons 6 with girls. The other thing is that I always have to put parentheses, even if the thing doesn't have any pieces. So the empty will have parentheses also. And the other thing that I do is I put the names first. I do new empty parentheses, new cons parentheses, new cons parentheses, new cons parentheses. Another change that I make is that in Java, we always put commas in between the arguments. And by tradition, we write down the kinds of things as capital letters. So I'll put down a capital E, a capital C, a capital C, and a capital C. So what I've done here is I've slowly turned a Racket data type, a Racket data instance, cons 6, cons 4, cons 2, and empty, and I've turned it into a piece of a Java program. Now, if I try to run this program, it's going to error. And it's going to error, and it says class list doesn't exist, and class empty doesn't exist either. That's because these things that we wrote down, we're just basing off the idea of what we'll eventually build, but they don't actually exist right now. And that's because these things, even though they were built in to Racket, they're not built into Java. Now, in Java, every different kind of thing, each variant, becomes its own class. So we'll write class empty, and we'll put the mustaches there for all the things that are inside of an empty. And we'll write class cons for the stuff that's inside of the cons. A list, however, is not actually a class, because a class is only for the variants, the ones that actually have pieces, the things that will be constructed as the program is running, like down here. The list, which is on the left-hand side, only exists to be an empty or a cons. And so because of that, in Java, it's called an interface. So we write interface of list. So an interface is either an empty or a cons. And we connect that by saying empty implements list and cons implements list also. Now, notice that when we wrote the data type definition, we said a list of ages is either empty or cons. So it sort of says the interface says what kinds of things are inside of it, whereas Java actually has us do the opposite. Java has us say the class is an example of an interface. There's not really any deep significance to that, although we may talk about it later in the course. Now, if we run this program, there's still going to be an error, but the errors will be less. And the errors come in, there are only 4 of them. And the first one says that there's no constructor for cons that takes an integer in a list as arguments. In fact, there's no constructor for cons at all. And it says that there's no function called total. There's no method called total. So let's implement our constructors. So empty doesn't take any pieces, and you don't need to do anything to make one. So it's very easy to write its constructor right here. And since there's really nothing in here, that's essentially what Java puts in automatically for us. So that's why there was no error related to cons. For our cons, however, we have to write down that we take in the age, and then we take in the rest of ages. And by tradition in Java, we write in camel case. Then, as we do with all classes, we save these things in the instance variables. And the instance variables we have to put down is there's the age, and there is the list of the rest of ages. So all we did is we took this idea right here that was in Racket, and we said that a cons is made up of these two pieces. The constructor takes those two things as arguments, and it saves them inside of this. So if we run this program, it will continue to fail, but there will only be one error now. The error now is that there's no method called total on the interface list. And that's because in our program down here, even though we're calling total on kids, if we look, kids was defined up here as a list. That means that when we look at the total function, it's going to look inside of list up here at the top of the program. And the interface doesn't say anything inside of it. So because it doesn't say anything, the total is not going to be there. So what we can do is we can write down the definition of total, or rather the contract of total. We say int total, and there's no arguments. Of course, we know that there really are arguments, because every method takes an additional argument, which we don't write, called this. So this function, it really takes in a list and returns an integer. But when we run this program, we're going to go from having one error to two errors. Let me show you which error is going to go away. This error down here is going to go away because now list does have a total function. But there's going to be two more errors. Can you think of what they're going to be? The errors are going to be that empty says it implements list, but it doesn't provide a total function. And cons says it implements list, but it also doesn't provide a total function. Let's run and see the error. When we run, it says, empty is not abstract and does not override abstract method total in list. That's a complicated way of saying that there is no total function. Let's write down the total function. We say int total, and then inside here, we can write something. So what's the total for an empty list? How can we figure this out? What's all the ages of all the kids that are talking in my bed right now? I'm sitting on my bed, by the way. This is an audience response time. I wish I could make it so you can see me at the same time as seeing my screen. I'm waiting for someone through the question and answer to say what I should put down there. I wonder if it's because there's like a delay that you are now hearing it, and I've been waiting for a long time. Well, what we want to put down here is return and then some number. Let's put in the number 0, because all the kids, their ages sum to 0 when there's none there. When we were honeymooners, we only had all our kids, they were a total of age 0. Now when we run the program, there's only going to be one error. Actually, it says total cannot implement. We have to write down public total, public int total. Yes, thank you, Nick. Ah, interesting. Yeah, there was a delay. Thanks, Paul, for letting me know. So, so we've got public int total for saying what the total inside of the list is. Ah, yes, that's a good idea. We can open up time. Thanks, that's a good idea. Elijah, we're getting we're getting the sum of the ages. That's the goal. And so done with that. New movie recording. Put it down here. Oops. That right there. Yes, Alexandra, I saw your question. Thank you. I saw this. Richard, yes, good idea. I should make it on the float on top. And we'll go back here. Okay. So we want to do the same thing for cons. We can put in some implementation right here. Now the implementation right here, however, it just says return 0. So when we run our program, it will actually run, as we see here, but it says the total age is 0 and it should be 12. So one of the things that you did when you were in 101, when you wrote a function like this, is you did what's called taking stock, where you write down all the things that you're allowed to look at inside of this function. We would write down this because that's available. We would write down this.age. We would write down this.rest of ages. And age is an integer, and list of ages is a list. And this is also a list. One other thing that we can do is, because this is a list, that means we can call all the list functions on it. We can call the list functions, and so we can call total on that, and that would be an int. And we know that we're supposed to return an integer. Let's try out some integers. We could return this.age. If we did that, then it would say that the total age is 6, but it should be 12. So that's not right. If we put in the rest of ages.total, and we would get 0. Why would we get 0? We get 0 because they're all returning it. So what we need to do is we need to take these two integers and combine them together. And when we combine them together, we get the answer. The total age is 12 and should be 12. So we have just implemented our first function on lists. So we've got our implementation of the cons right here. We've got our implementation of the empty right here. And we've got the list one right there, the definition of a list. Now, to help you see how this connects back to what you did in Racket, let me write the function in Racket. In Racket, you would have written this. Define total of L. And you would have wrote down con empty L. Then you would have written a 0 here. And then you would have written an else. Then you would have done plus first of L, total, rest of L. That's the program that you would have written in Racket. Now notice that this function right here, the total, contains inside of it the definition of empty, and it contains inside of it the definition of what you do for a cons. So it combines this piece right here, combines this piece right here, and it combines this piece right here. In Java, however, you separate out each one of those pieces into their own class. Essentially, all the various functions that you'll ever write about lists, all their con sides will be all together, and all their empty sides will be all together. And the only way that you'll connect them up through the definition of total is through the interface right here. Can someone propose another function on lists that we should write? Propose as a question. And I'll like wiggle and stuff like that while I'm waiting for you. The plan is that we're going to write another function on lists, and then we'll write the binary trees. I've recently been listening to the Yellow Magic Orchestra. They're kind of like the original synth pop band. It's pretty cool music. This delay is killing me. I think also that like in class, you would see someone else, getting ready to do the answer or something like that. And so is empty sorting algorithms. Is empty is really easy. Sorting algorithm, maybe we could do that. That's a little complicated. Let's see what the second one is. Thank you, Paul, for being the first one to say something. But yeah, I was going to say that, when you're in class, you can like look around and see that no one was answering. You know what I mean? All right, I guess we'll do remove. Yeah, let's do remove. Actually, given the context of the ages, that's kind of gross. What would remove mean? Let's do a simple sorting algorithm. Let's do. Yeah, sorry, Noah, I'm going to delete your question. All right, let's do sort. So what does sort do? Sort takes in the list and returns a list. We'll say list sort. Nth element, that would be a good one, Brandon. But Paul beat you to it. Let's sort. Ooh, I don't want to do that. Okay, so let's write an example. So we want to say, we'll say kids is kids, and then we'll say sorted kids is kids.sort. Okay. Now that actually reminds us that one of the things that's very useful, so by the way, this is going to be all messed up, so at the top of the program, we're at the bottom of the program where we see the sorting function. When I run this, it's going to error because the sort isn't implemented everywhere. Let's do a really dumb sort function first. So we'll say public list sort, return this. That is a list, so it certainly is allowed. Okay. Now it says kids is cons at blah blah blah. Sorted kids is cons at blah blah blah. So it's very like that's not really a convenient way to look at the kids. Something that's very nice to do inside of Java is that there's a special function you can write called public string to string. And what you get to do is you get to return a string that you want that looks like the thing. Now, what you can do is you can make it look cute like this. So I'll say that an empty will print out as empty brackets. And we'll say that a cons like string to string will print out as this dot age plus colon plus this dot rest of ages. Now if we do this, then they get printed out in this cute way down here where it says 642 blah 642 blah. So that's nice. What I personally like to do the most when I write these two-string functions is I like to have it print out as the Java program that would produce the value. So I say empty returns new empty, string new empty. And what this one does is it will do return new cons plus this.age plus comma. Then I'll put this in parentheses. Actually, yeah, this dot rest of ages. Really slow for a second. And then the closing parenthesis there. That. So now when I run it, the way it gets printed out is as whatever actually constructs this value. And I think that's super convenient. So you can, look at your program, you can run your program, and you can like copy and paste this in and see what it would look like. I think that's really nice. All right. So now we can see that kids is 642 and sorted kids is 642, which is clearly wrong. We want it to be 6. We want it to be 246. So how can we do this? So let's do insertion sort, which is probably the sort that you learned, when you were in 102. So Insertion sort relies on another function called insert, which takes an int and returns a list. So we have an int of, we'll call it x. So actually let's call it I. We take a list, we take an integer, and we'll return a new list. So let's implement that for empty. But to implement it for empty, we return a new cons with I and this. Because the new age is the one that we see, and the thing afterwards should be this. And for cons, sorting is very easy. We do this dot rest of ages dot sort dot insert this dot age. So we sort the rest of the list, and then now that we have a sorted list, we insert this age into the right spot, whatever that right spot is. Now this implementation of insert will work, although it's not correct. Yes, Alexandra, all the code is always available for this for the class. Let me see if I have it open. Down here, see there's a link right here to code. That's the code that we wrote in the lab. This is the code from the first day of class, and there will be a link right here for the code that we write today. And there'll be, one for the whole semester every day. Right here. All right. So when I do this version right here, where insert just puts it at the top all the time, it still says 642, which isn't what we want. What we want to do is we want to say if I is less than this dot age, then do that. Otherwise, return a new cons where this dot age is first, and this dot rest of ages has had this value I inserted into it. And when you do this, we will get the sorted list. So see, sorted kids is 2, 4, 6. So we've just implemented insertion sort, and in the process we learned about 2 other things. We learned about how to do toString functions, which is a very convenient way to look at what objects are. And we learned about how you can combine a bunch of functions together to get some job done. So in this case, sort relies on insert. Notice that our insert function returns a new cons right here. And it doesn't change the old one. That makes it pure, which means that every operation you do doesn't change the old value, it returns a new one. This is very important in modern computers that rely on concurrency, which is when you run lots and lots of programs at the same time, and lots of things happening inside of one program. Because they don't actually modify anything, that means that if 2 programs start trying to do the same thing at the same time, they won't hit each other and conflict with one another. When they create new values all the time, this means that they are guaranteed to be separate from one another. So that's one of the reasons to do this, and this property is called purity. I'll put a little note here. Notice that insert is pure, meaning that it always returns a new value rather than modifying the old. Let's go through the same process with binary trees. With binary trees, we have to start off with BST example function call. Okay. So let's think of an example binary search tree. I find it easiest to think of examples by writing them down in so Binary search tree is, you've got nodes which point to other nodes, and there's a left child and a right child, and then there's something in the middle. So there's the left, middle, and right. And the middle is a value. And the value is typically called the key. And the left is a whole tree, and the right is a whole tree too. But when I write these things down, I often find it convenient to think about them from the bottom. So we'll think about the bottom. So BST, we'll call this bot. And at the bottom, you have something that has no pieces, so that's called a branch. So we'll say new branch, sorry, a new leaf. Okay. Then we'll have, something, we'll call this T0. And that'll be a new branch where the bottom is on the left, something is in the middle, and the bottom is on the right. And let's put right there a 1. So let's label this T1 so that we'll remember that 1 is inside of it. Let's make it so that on the bottom of the whole tree, we have 3. We have 1 and 3. And then we have 5 and 7. We've got 1, 3, 5, 5, and 7. Then, above 1 and 2, we'll make 2 there. So to 2's left will be T1, and to 2's right will be T3. Then above 5 and 7 will be T6. And to its left will be T5, 6, 7. Then at the very top, we'll have T4, and it'll have T2 to its left and T6 to its right. This is an example of a binary search tree. If we were to draw it out, we would have 4, and we would have 2 and 6. Then we would have 1, 3, 5, and 7. That's a little example binary search tree. Binary search trees have the invariant that everything to the left is smaller than the head, than the top, and everything to the right. And everything to the right is larger than the top and everything to the left. Now, an example function that we might want to call is we could say system.out.println the smallest thing is, we could say t4.smallest, and then we'll say should be 1. Good? All right. This is actually a funny example. This function is going to be hard to write, surprisingly. Well, it'll be awkward to write, but we'll do it anyways. This is the first one I thought of. So as before, we've got this full example worked out. We have an example of the data structure, and we have an example function call. Now, when we run this, it's not going to work. We're going to have to implement the various pieces and the function. So let's write everything down. We'll have the interface, BST, and it's going to have a function that's called smallest. And we'll have the implementation of leaf, which implements BST. And it has no pieces, so it's really easy to write its constructor. And let's implement 2 strings as we go. We'll say that this is return new leaf. And we'll write down what its smallest is. And this is where it's awkward to write the smallest function, because what's the smallest thing inside of a leaf? There's a few ways of going about this. We could have an error happen. We could say throw new runtime exception no smallest in a leaf. Probably the most Java-y thing to do. Then we can write down class and branch implements BST. Then we'll have the BST for the left, the integer for the middle, and the BST for the right. Now, as I mentioned, the middle is often called the key. And we'll write down a constructor, branch, BST left, int key, BST right. We save them. This.left equals left, this.key equals key, and this.right equals right. Then we'll write down our toString function. String toString. Say return new branch. We write down this.left plus comma space plus this.key plus comma plus and this.right plus close parenthesis done. Now we write down public int smallest, and we have to return some number. Let's just return this.key for now. Good. Now if we run this program, oh, there's an error. Be a plus right there. Now we run, and it says the smallest thing is 4, and that should be 1. So let's go look. So notice that it says the smallest thing is 4. So this right here evaluates to 4, but it should be 1. Why does it evaluate to 4? So we call smallest on T4. So T4 is a branch. We've got to look at the code for branch. And it returns this.key. So inside of branch, left equals T2, key equals 4, and right equals T6. And so we're returning this.key, which is wrong. Because if we return this.key, then that means that we'll always return 4. But we actually want to return 1. Now, where in this tree is the 1? It's right here, which is on the left of T4. It's inside of T2. What we should be doing is returning the smallest thing that's on our left. Because the thing about binary search trees is that everything on the left is always smaller than the middle. So that means that the left is always where the smallest thing goes. So we should really do return this.left.smallest. Now when we run this, however, we have an exception. And it says, exception in thread main, Java language runtime exception, no smallest in leaf. The problem here is that if every piece of the program always returns what's to its left, and if we go down and look, it says 4 will say we'll ask 2 smallest, and 2 will say we'll ask 1 smallest. And really underneath here at the bottom, there's more links like this. And every single one of those has bottom, 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 bottom. And bottom always says there's nothing here. And bottom, by the way, is really a leaf. So there's a leaf, leaf, a leaf, a leaf, a leaf, 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 leaf. And you look at all those leaves. There's all these leaves down there. But the problem is that leaf will throw an exception. So what we can do is we can say, so clearly the problem is that sometimes we want to return the key and sometimes we don't. What's the difference? Well, we should always try to return the smallest. But if we can't, then we want to catch a runtime exception. This isn't really right, this. And then when that happens, then we want to return that. Is that what we did? I've got touch runtime exception. Yeah. Oh. E. There we go. Now it says the smallest thing is 1 and should be 1. So in Java, you can try to do something, and if it fails, then an error will be thrown, and you can catch that error. So it throws the error, and you can catch it. And then when you catch it, that means that the error doesn't happen anymore. And you can run a new part of the program, and in particular, the thing that you can run the thing that you can run is this code right here that will run, that will grab whatever the key is. So this is an example of writing a function on binary trees. We went through a very simple process. We came up with an example of the data structure. We came up with a simple test case. And then we came up with a implementation by first putting it in the interface, then implementing it for each one of the variants. Then, in each variant, we often will use the implementation for other variants like this. Now, in your code for the finite sets that you'll work on for the first assignment, you'll be using binary search trees. You'll be implementing functions like insert into this binary search tree and look something up and count how many things are inside of it. And this smallest function is sort of like a template for what you'll be working on. I highly suggest you do not copy this code, but you start from scratch and write your own so that you can see, so you can sort of go through the experience yourself.
Daddy, look what I made. Science.
That's cool. It looks like a volcano.
It is.
Yeah, I'm still on the call though. So.
There's lava coming off.
Okay. So what we can do is we can go over in more detail anything we already covered, and maybe we could write another example of a binary search tree function. What are your preferences? I'm looking at my phone to see if I can see any mail coming in from any of you saying that something is happening. Should we do lookup inside of a binary search tree? Or insertion? I'd like another example. Thank you, Justin. What should we do? We can do insertion. We can do membership. We can do something else. One thing that I like that's very neat is the predecessor and successor. So what comes before and what comes after, those are strange ones to do. Can you talk a little bit about deciding to make BST an interface and having 2 classes implemented? Should we take that approach to design? Okay, so Nick, so let's go with Nick's. Okay, so yes, definitely. You should always make your interface. You should always make an interface for every set of classes you write in this class. So no matter how many different things you do, you should always define an interface. Even if there's one thing, you should still define an interface, because you don't know if in the future you're going to want more. And you should always implement your classes to say, here is the interface that I implement. It's useful for a check to make sure you don't forget anything. And in your code for the finite sets, you'll probably use two, because there'll probably be a leaf and a branch, because that's kind of what binary search trees are. For other things in the class, there might be other interfaces that you'll use, and we'll spend quite a bit of time talking about binary search trees, or about interfaces and interface-based design generally. So let me hit done on this question. Now it looks like you can vote for questions, so people have voted for a quick overview of exceptions. Although they say after more examples, and then the other ones are for insert. So we can let's do insert first, and then we'll do the exceptions. So to do insert, we'll write down the contract. So insert and integer x. So again, the contract for this is insert takes a BST and int and returns a BST. And let's come up with an example. So say that system.out.println pi is, and we'll do t4.insert 3.14. Actually, these are integers, so we can't do that. What's going to go in between, though? This is kind of like complete, which is kind of annoying. Yeah, because the only thing that we can really put in that we don't have is 0 and things that are big, like 8. So let's change this so that rather than 4 at the top, let's put 6 at the top. Change this to 7, and then that to 8. So let's just change this. So 6, 7, 8. So that's 8, 8, 7, 6, and 7 is to the right. That way we can insert 4, and it'll go down there. Okay. So see, 6 is smallest is 1, and call it 4. So we'll insert in 4. Right, and we'll be able to look at it and see that it's there. We could make a more interesting way to test this, but we'll use our eyes for now. Okay, so to insert it in, I've added it. We wrote our example, and we added it to our interface. So that means that when we run our program, it's not going to work because insert isn't implemented for these things. So public int insert, sorry, BST insert int x. There you go. So how do we have a leaf with nothing in it and insert something in? Well, we know that we're going to get a node, because the reason that we're going to have a node, meaning a branch, is that only a branch actually stores anything. A leaf never stores anything. So we're going to have something to the left, something in the middle, and something to the right. Now, what goes in the middle? Well, it's the thing that's being stored, which in this case is the x. Now, what goes to the right? Well, there's nothing to the right and nothing to the left. So that means that the thing that goes in here is just an empty. And we have an empty sitting around. This is an empty. So we can do return new branch, this x this. So that creates a new branch with nothing on the left and nothing on the right. Let's look at the branch. For branch, we don't know where it's going to go. We have to decide that based on what its relationship is with the thing at the top. So we want to say if the thing at the top, right, this key, if the key is equal to x, then we want to do one thing. And one thing. If the key, let's write this the other way. If x is equal to the key, if x is smaller than the key, and then otherwise. These are our three cases for an insert. It's either equal, smaller than, or greater than. And I'll put a little comment right here that says x is greater than this document. Now, if it's equal to, then we don't actually need to do any insert because the thing is already in the binary search tree. So we can just do return this. Alternatively, we could change this right here into a less than or equal and leave this case out, but that's a different meaning. You do this, this version, if it's a set, because if you have a set of things and you try to insert in something that's already in the set, well, you're done. You don't need to do anything. It's already there. Now, what do we do if it's what do we do if x is less than the key that's already there? Well, that means it needs to go on the left. So what we need to do is return a new branch where a new branch where the key is exactly the same and the right is exactly the same, because those don't change. This is indenting really funny. Believe me. So the key is exactly the same and the right is exactly the same, but the left is different because we need to now insert this thing on the left. And wherever it goes on the left, that will return a new binary search tree that has the thing at the appropriate place on the left. And so that'll be our new left. We'll keep the key and the right the same. And obviously, when we insert it, to the right, it would be the opposite. That left would stay the same, and right would be the one that would be different. You have a baby?
Yeah.
So when we run this program, it's not a statement. Oh, whoops. That's the problem. I have to write else if. That was silly. That's why it indented funny. When we run this, it says for is, and this is a little bit hard to read, but we have so we have 6 at the top. Then to the right is 7, 5, and 8. And to the left is 2, with 1 to the left, 3 to the right, and then to 3's right is an empty, with 4 and another empty there. So it got put in the correct spot. So we have an example of binary search tree insertion. Okay, let's close this one. Let's select false question, mark it as being done. 5 is out of place, isn't it? It's to the right of 6. Another example. Oh yeah, you're right. We put the 5 up there and the 6 down there. Notice that our code didn't actually care. But yes, you are right. We should have.
Have some shut that didn't work like that.
She knows that it was wrong. That's what she's saying. All right. Okay. So that's another example of doing insertion. As we did before, we started with an example with an idea of what it should look like. Then we added it I'm just doing page up. We added it to our interface, and then we had to implement it for each different kind of thing. It was easy to implement it for leaves, and it was more complicated to implement it for branches, where we had to look at all these different situations. Basically, all your functions on finite sets will look kind of like this. There will be something that you do when they're equal, something that you do when they're not equal, and something that you do when, or something you do when they're less than, something you do when they're greater than. Unless you can make it so that the cons case is always the same, or sorry, the branch case is always the same. So for something like union, there's an empty and a cons that are just one thing. But for something like remove, remove is more like insert, and member is more like insert. Now for an overview of exceptions. Let's do an overview of exceptions. There will be a time in the class that we go into much more detail on how to design programs with exceptions, meaning how to decide whether to put an exception in your program. But for now, what I'll do is I'll talk about when you, like how to actually put exceptions in the program. Basically, what exceptions do is they allow a program to return something different than what it says right here. So for instance, main right here says it returns void. And if we look at that example from before, the smallest says that it returns integer. Notice that this function right here, this implementation of smallest, please don't cough on my computer. That doesn't look good. This implementation right here of smallest, it doesn't return any integer. There's no integer that it is returning. So at a high level, what exceptions do is they allow programs to get out of whatever promises they made. And in this case, the promise that was made was that it returns an integer. Now, the way that it does that is by writing throw and then the value that you want to return. So here we're throwing new runtime exception. So essentially, return and throw, they kind of have the same purpose, whereas return returns the thing that you promised, and throw returns something else. Now, here what we did is we returned a new of this thing. What we could have done, or let's see if we could have done this. Let's say, throw the string none, as an example. Would this work? And it says no. It says incompatible types. It says found string and required throwable. But everything that gets thrown has to implement the class or the interface throwable. So see how branch implements binary search tree? There's an interface called throwable, and the only things that you can throw are things that obey that interface. And runtime exception is an example of something that does implement that. And what runtime exception does is it's a class that has one field, which is a description of whatever the error was. There's a large number of example exceptions that you can do. Like if we Google, let's go to Google. You can say Java exception types. Then there's this thing built in. And so like look at all these built-in exceptions. And they're all for different reasons. And look at that, runtime exception isn't even on the list. Yeah, I don't see it. Yeah, so that's what that's how you use exceptions. Oh, sorry, one more thing, which is that because this function is now returning abnormally, if the abnormal return, it sort of like percolates up the program. So like, let's look at a little example. Inside of smallest, that's right here, return this left dot smallest. So if the thing that was on the left was a leaf, then that means that it wouldn't be returning an integer. So this program now could not return that new arithmetic exception, or sorry, the new runtime exception, because that's not an integer. So this program would essentially break at this point because it is expecting to receive an integer and it didn't. So whenever one function, let me write this down to be precise. Whenever f calls g and g throws e, then f will throw e. Basically, the throw is like infectious. It will keep happening. Except when f catches things like e. And the way it catches things like e is by writing so try, and then inside of these mustaches, you write down the call to g. And the catch, you write down the kinds of things that you want to catch. So in this case, it is catching runtime exceptions, and it's naming them e. So any exception that's caught will be named this, and now this code can go do something else. Now in this case, it returned this.key, but it could do anything. It's just a way of saying that this code on this line might throw an error, and here's what will happen in the case that it does. I hope that was a good enough yet brief explanation of how to do use exceptions and how to use basic data types in Java. We talked about lists and we talked about binary search trees. The binary search trees will be very useful in the program that you write in class. So I think this was okay. The question and answer thing worked out pretty good. I wish it would have been faster. What I'd really like is to be able to see people and have them like connect in, when they have a question. But we'll have to figure out how to do that for next time that we need to do this. Sorry. As far as the finite set assignment goes, does a finite set have a binary search tree? Nick, I would say that a finite set is a binary search tree. That basically, in the code for the assignment, basically finite set is an interface, and I've told you here are all the functions in that interface, and you'll write two different classes. That's the way that I would do it. Because there's nothing that a finite set will do that a binary search tree doesn't do, so why bother making it a separate thing? Are there any other questions? Any other questions? It's very cute. Okay. Well, in that case, we'll stop. Let me turn off the video here and stop screen sharing and go back to the video. Okay. I'll be posting the notes in a few minutes, and then I'll also post an archive link to this so you can watch it again. Yeah, so I'll see you all on Wednesday. Bye.